Over the next two videos, we're going to look at a couple of quite similar problems, which are going to use inequalities, and we're going to look at how we can solve them using logarithms. But each problem I'm going to look a slightly different method with the logarithms, but you can apply both techniques to either problem. So for the first one, we're going to have a look at using the natural logarithm. So for this problem, we're given a geometric progression has a first term of 50,000 and a common ratio of 0.9. Which term is the first to be below 10,000? So we're looking at which terms, so we're looking at the position of the terms in here, and so we're going to need to use the nth term formula. Now let's extract some of our key information then. So we're given our A, which is our first term, which is 50,000, and we're given our common ratio R, which is equal to 0.9. If we use our nth term formula, we can say that we have A, 50,000, multiplied by our R value, 0.9, to the power of n minus 1, because we don't yet know n, we're going to find n. And we're looking for when this term is the first one to be below 10,000, or in other words, when we're looking for this to be less than 10,000. So we're going to need to deal with this inequality. Well, we don't like this multiplication of 50,000, so we can move that and we divide it on the other side. So 0.9 to the power of n minus 1 is really going to be less than 10,000 over 50,000, which simplifies to 1 over 5. Now we can take logarithms of both sides, and for this problem I'm going to take natural logarithms of both sides, such that we have the natural logarithm of 0.9 to the n minus 1 is less than the natural logarithm of 1 over 5. Well, we can use one of our log laws, such that the n minus 1 moves down as a multiplier from the power. So we've got n minus 1 times the natural logarithm of 0.9, which is less than the natural logarithm of 1 over 5. This natural logarithm of 0.9 is a multiplication, so when it moves it becomes a division, such that n minus 1, on this side we're going to have the natural logarithm of 1 over 5 divided by the natural logarithm of 0.9. Now I haven't yet put the symbol, because actually our symbol is going to reverse. It's going to be when we're looking for when this is greater than. Why does that happen? Well, we want to note that we get a sign change as the natural logarithm of 0.9 is less than 0. It's a negative value. And if you divide by a negative value, when you've got an inequality, it's going to switch the order of the inequality. Okay, so that's important. So our inequality sign is going to change. So we swapped our inequality. Final bit of rearrangement then, that n is greater than the natural logarithm of 1 over 5 divided by the natural logarithm of 0.9. When the minus 1 moves, it becomes a plus 1. Well, we don't really care for it in the natural logarithm form, so let's convert that into a decimal, and that n is approximately greater than 16.276. Now, because n represents terms in the sequence, n must be an integer value, and to satisfy this inequality, we are looking for the lowest integer value, so n must be equal to 17. It's the first integer value that satisfies this inequality, so n is equal to 17, and that would be the position of the term. So therefore it's the 17th term as our position, but actually because it says which term, we can work out a value for that term, and really we're just looking for U17. So our n value is equal to 17. The A and R haven't changed, we've still got 50,000 for our A, and 0.9 for our r. So U17 is equal to 50,000 times 0.9 to the power of n minus 1, so 17 minus 1, which is equal to 16, which if you put that into your calculator, you end up with 9,265.100944. We've got a not so nice decimal there, but that's actually the value of the first term, which is below 10,000. Now you can check this, because if you put n equals 16 into your expression here as the power, so 16 take away 1, so your power would really be 15, you'll find that it's actually above 10,000, and then the 17 then brings it below the 10,000 mark. So that can be used as a check at the end. But that's how we can solve this one using the natural logarithms.